without further delay, let me go ahead and talk to you about the common ion effect. And you guys already know this because we talked about it in equilibrium, okay? When you have a common ion, and the common ion has to do with the chemical that you start with, the reactant that you start with. And remember, the reactant that you start with, in most cases, will break apart to its ions. And the ions are the common ions, okay? That's why it's called common ions, because when it breaks apart, it generates these ions. And if you already have those in solution, then it's going to cause that equilibrium to go in the reverse direction based on Le Chatelier's principle. So you guys can see how important equilibrium is in acid-base chemistry. If you understand that fundamentals, then acid-base chemistry is not as difficult as it may seem, especially if you start later on when you go into apply to medical school and you do the MCAT. I was talking to former students and I asked them exactly what part of Chem 201 would be in the MCAT exam. And they said there's a lot of acid-base chemistry. And the reason why is because acid-base chemistry plays a vital role in body chemistry and human health. And we'll see that later on in this discussion when we talk about buffer systems in the body, okay? So like I said, you guys already know about the common ion effect and the fact that when you have a common ion in solution and you put that chemical in and it dissociates and it produces that ion in common with what's in solution, then it causes that equilibrium to go in the reverse direction. It causes the dissolution to be inhibited, to be not as efficient because of the Le Chatelier's principle. So again, those are the fundamentals that we learned back in chapter 15. So let's take a look at exactly what we can do with this common ion effect / buffers. Okay, so the common ion effect, again, what happens, like I said, it decreases the dissociation. When I give you terms like dissociation or dissolution, you got to make sure that you understand the physical process of that, because if you're still processing it in your mind and I'm using these things freely, then it's hard for you to make that connection. Okay, so when you put a chemical in solution, it will, especially acids, it will dissociate. Some 100%, others less than 100%. The ones that are less than 100% will be weak acids or weak bases. The one with 100% dissociation are going to be strong acids and strong base. So we can actually decrease the dissociation even further, even if it's a weak acid, by Le Chatelier's principle. So here's an example. We have acetic acid. It's pure. It's just plain water. And you put a little bit of vinegar in there, or you put a little bit of acetic acid, and you're trying to figure out the pH of the solution. That's a typical problem that you guys should know how to solve. What you need to know is A, the concentration of that acetic acid, and B, what is the Ka of that acetic acid. Okay, if you know that, then you can make the assumption, okay, the water is going to be about 20, 25 degrees. So I know the Kw is 1 times 10 to the minus 14. That's the other thing that you need to know. Okay, what is the Kw? Because if the Kw is not 1 times 10 to the minus 14, then you've got to remember that pH plus pOH equals pKw. Whatever the Kw is, that's what those two values equate to. Okay, so in this particular case, we have it at 25 degrees. You need to make that assumption if nothing else is stated. Okay, if nothing else is stated and you're not giving that information, you got to make that assumption. Otherwise, you can't move on. Anyway, we have this acetic acid here. We know the Ka is 1.8 times 10 minus 5, and the concentration is, in this particular case, 0.10 molar. This thing will be, you guys know how to solve this. You just go straight to this equation. H plus equals the square root of the Ka times the acid concentration. Okay, you don't have to do the ice table. The ice table certainly is the fundamentals, but when you derive the equation for H plus, that's what you get. Please remember that because it'll save you a lot of time. The Ka is 1.8 times 10 to the minus 5. That's a small number. You guys can make that assumption, that simplifying assumption. And the concentration is 0.1. That's pretty big. Okay, so this is going to be a valid simplifying assumption. So when you do this, the hydrogen ion concentration, try it. It's going to be 1.34 times 10 minus 3. So the other question that can be asked is, what is the percent dissociation, alpha? Well, that's just this number, 1.34 times 10 to the minus 3 divided by the initial concentration. Remember, it's the amount that dissociates, the amount of hydrogen that's produced, the amount of ions that is produced divided by the original concentration. The original concentration is 0.10. So this is basically it right here. And you see that as characteristic of a weak acid, the percent dissociation is only 1.34. That is, for every 100, only 1.34 will dissociate in solution. It's a weak acid. Now, what happens if we put into solution a common ion? And you might say, okay, well, how do we produce a common ion in these things? Well, this is the way it's done. You have a beaker again. Okay, you put acetic acid in here, and we abbreviate acetic acid because we're lazy, okay? HAC. AC stands for the acetate ion, okay? Get used to it. We do that especially a lot in organic chemistry. So HAC stands for this guy right here, where this anion right here is just represented by AC, okay? Acetate. Well, how do we get a common ion here? Well, we put a chemical like sodium acetate. Okay, sodium acetate is a salt. It's going to be a solid item. Put it in there, dissociate. You got sodium. It's going to be you guys know this as a spectator ion because it just watches the action. And the acetate is the common ion of the acetate and acetic acid. That's how you get this common ion effect. What you have effectively here is something called a buffer. Okay, a buffer. So look at this right here. Let me clear this. You can see that. So now we have acetic acid and we have a common ion, sodium acetate, same concentration. What is the pH of the solution? Well, when we do the ice table, this is the ice table right here. I'm going to show you the ice table, and then once you recognize it's a common ion, you just cut straight to the Henderson-Hasselbalch equation, okay? Because in your mind, I hope in your mind, you guys already know the fundamentals, the ice table, but we just go straight to the equation that gives you the vital information that you need, okay? So here's the initial concentration. The initial concentration of acetic acid is 0.1, but the acetate now is 0.1 because when you put sodium acetate in here, and the sodium acetate is 0.100 molar. Remember, sodium salts are 100% soluble. So it's 100% of the time, it's going to dissociate, okay? Unlike the acid, where only 1.3% of the time it will dissociate. Well, for salts that are very soluble in water, you put in 100, you get 100 ions of the cation, you get 100 ions of the anion. Okay, don't overthink it. Don't overthink it. Because according to the solubility rules, these things are soluble in water. Alkali salts, soluble in water. I know there's a lot of things to remember, but that's just part of chemistry. You got to remember all these little rules. But I'm telling you right now, if you've got an alkali salt, put it in solution, it's 100% soluble in water. So that means 0.1 molar goes in, 0.1 molar acetate comes out. Okay, so that's the initial line right here. That's the initial line. Then we go ahead and process our ice table. Okay, we go ahead and process our ice table minus X, because that's the amount of acid that dissociates, plus X in terms of the acetate. and then plus X in terms of the hydronium, because when the acetic acid dissociates, it's producing the acetate and the hydrogen ion. Okay, so here it is right here. This is the equilibrium condition right there. And then we stick that into the mass action expression, products over reactant. So when we do that, what we have is we can assume that X here is much bigger than 1 times 10 to the minus 7. We do a lot of assumptions in acid-base chemistry. You just have to be comfortable with it, okay? So what we have here essentially is, and then we can also assume here that X is smaller than 0.100. We make assumptions both ways. We say X is bigger than this number, X is smaller than this number. Usually that will work out, especially for the problems that I give you, because these are going to be classic problems. So when we stick it into the mass action expression, the hydronium ion concentration times the acetate ion concentration, okay, over the acetic acid concentration, that's just the equals the Ka. Why is it a Ka? Because it's the acid generation reaction. Whenever you're producing hydronium, the equilibrium constant associated with that is Ka. If you're producing hydroxide, then the equilibrium constant associated with that would be a Kb. Here we're producing hydronium, okay? So this number is X, this number is 0.1. And if we assume that X is much smaller than 0.1, okay, then this number is also 0.1. Guess what? That and that cancels. So what is our hydronium ion concentration? It's just equal to the Ka, which happens to be 1.8 times 10 to the minus 5. Okay, so that's your hydronium ion concentration. That's H3O plus. You guys are going to be grateful when the common ion is equal to the acid concentration at equilibrium. Why? Because it really simplifies the problem. It really simplifies the problem. So what we have here is the hydronium ion concentration. It's right here, 1.8 times 10 minus 5. The pH, you take the negative log of that, is 4.74 versus 2.87 right here when you didn't have a common ion, when you didn't have sodium acetate in there. What is the percent dissociation? Remember, it would be 1.8 times 10 minus 5 divided by 0.1, the original acetic acid concentration. You do that number, you get a percent of 0.018, less than 1/10 of 1%. Okay, so look at the difference here. If you have a common ion, only, like this is like 18 in 100,000. 18 in 100,000 will dissociate versus 1.3 in 100. Okay, so indeed what happened, true to Le Chatelier's principle, the equilibrium was shifted in the reverse direction. That means that the acid stayed intact. It didn't want to dissociate, and only a very small amount dissociated. That's what we talked about in the common ion. That's essentially what happens in a buffer. The key thing that you have to remember in a buffer is that this, let me change my pen, this and this has to be present in the same solution. It has to be present in the same solution. If it's not, then you don't have a buffer. You don't have a buffer. Okay, so that's an important concept to remember, because then you can make, you can jump to the main equation that deals with buffer, which we will see next. Okay, so the equation that you will see is this right here. This is the equation that we had when we put in the mass action expression. Remember, the mass action expression is just this. Ka equals acetate ion, hydronium ion over the initial acid. That's just the mass action expression for the what we talked about in terms of acetic acid. Now, what do they usually ask in acid-base chemistry? The general question that is generally asked, like maybe 80% of the time, is what is the hydronium ion concentration? What is the pH? Okay, in an acidic or basic solution, that's what you want to know, because when your acid concentration or your pH gets out of whack, then it can mess up your system. It can mess up your experiment. It can mess up the system that you're studying, especially if it's a biological system. So the question that generally is asked is, what is the pH? What is the hydronium ion concentration? And so if we solve for H3O plus in this equation right here, we get this. Ka times the acid divided by the conjugate is equal to the hydronium ion concentration. Okay, and what did we say? We also want to know about the pH. Well, to get the pH of that, you need to take the negative log of both sides. You need to take the negative log of both sides. If you take the negative log of both sides, the negative log of hydronium, isn't that just the pH? Yeah, it's just the pH. And then that's equal to the negative log of this whole term, Ka over the acid. I'm just going to abbreviate acetic acid as HAC because I'm lazy. Okay, that. And then you can do the distribution. You can do the negative log of that, and you can do the negative log of that. Okay, and when you take the negative log of Ka, guess what? Guess what you got? You got the pKa. Okay, you get the pKa. And then you also have minus the log of the acid over the base. But we don't like negative signs. We don't like negative signs. So we're going to make that a positive. And when you make that a positive, we switch these two right here. Okay, we switch those two. So when we switch those two, this is what happens. Because we change the sign. Please keep that in mind. We change the sign. Now that becomes the conjugate base on top and the acid on the bottom. Okay. And guess what that equation is? This is called the Henderson-Hasselbalch equation. So if you're going to be asked what is the pH of a solution that has common ion, just go straight to this equation. Saves you a lot of time. You don't have to deal with the ice table. You don't have to deal with thinking about what assumptions I'm going to do. You just go straight to this equation, and like magic, you get the pH. Okay, it just works out that way. And we do this a lot because we need to know the pH of the solution. We need to know the pH. Now, there are exceptions where this is not valid. You got to know that. That's if this is a fairly big number. If Ka is a fairly big number, what do I mean by fairly big? 10 to the minus 2, okay, 10 to the minus 1. You guys know that simplifying assumptions would not work if the dissociation is pretty efficient, okay? It produces a lot of hydronium. Then your simplifying assumption won't work. Or if the concentration, initial concentration is very, very small. Remember, the simplifying assumption is valid when the efficiency of that reaction is very small. So you have an equilibrium constant that's very small, 10 to the minus 5, 10 to the minus 8, 10 to the minus 20th. Okay, and the concentration is somewhat large, 0.1, 0.01 might even work. Okay, so the stuff that we learned from equilibrium is still valid in terms of acid-base chemistry, but in acid-base chemistry, we deal with weak acids so much that we can make this simplifying assumption, and we can just go straight to this is called the Henderson-Hasselbalch equation. We can also do the same thing if we have a base. If we have a base, we have like NH3 in water, and we have a common ion with NH4 plus. Okay, so we could put NH4 plus like through ammonium chloride. Okay, so we have a common ion there. Then the Henderson-Hasselbalch equation for that would be POH equals PKB plus the log. And now these two is switched. These two terms are switched. It'll be the acid on top and the base on the bottom. It'll be like that. Okay, so everything's just switched because we're now calculating POH. So and then of course, you guys know how to calculate the pH from that, because the pOH plus the pH equals pKw. Okay, so there's a lot of things that you need to remember in acid-base chemistry, but it's stuff that we've already covered, so it shouldn't be that difficult. You're just connecting the dots. It's not new. Everything's sort of related. So let me clear this so that you guys can see this. This is basically what I just derived for you, right? Okay, conjugate base, Cb, or AC minus, if we're talking about acetic acid, over the conjugate acid. They have to be conjugate pairs. They have to be. What are conjugate pairs again? They're chemicals that differ by one hydrogen. They differ by two hydrogens, they're not conjugate pairs. They differ by one hydrogen. Okay, so keep that in mind. Here's the equation that you guys will use. So the Henderson-Hasselbalch equation is really the go-to equation once you recognize that you have a buffer. It saves you so much time. And you'll see that once we start generating titration curves, okay? There's actually two ways to generate a buffer system. The first is what we've talked about, okay? I wanna explain this to you. And the reason why I want to explain this to you, because probably that's a question I've asked in the past. Let me go with this. Ways to generate buffers. Solution. The first is a classic one. You have a solution, beaker water, and what you put in here is the acid and its conjugate. And you usually introduce the conjugate through its salt. Now, what will happen is that this solution will also have the acid and its conjugate in the same solution. Okay, so once you have that, you should recognize, hey, I've got a buffer. I can go straight to the Henderson-Hasselbalch equation if my simplifying assumptions are valid. Okay, no problem. The other way to generate a buffer is what we do in the lab all the time. Okay, we have a beaker. Okay, and we have an acid here. And right now that acid is not a buffer because all you have is the acid. Yeah, the acid will dissociate and form acetate, but initially, you got to remember, it's the initial line in which you have to have the acid and the common ion to have values. If the initial line has 0 for the common ion, it's not a buffer. It's not. It's got to have, in the initial line in the ice table, you got to have values for both the acid and the common ion. Then it's a buffer. Okay, so how do we generate a buffer if we just have an acid in solution? Well, we can generate a buffer by titration. What happens is that this will be a strong base like sodium hydroxide. Now, what will happen is because sodium hydroxide is such a strong base, it will demand that weak acid give up its hydrogen. Okay, it'll give up its hydrogen. And as long as you're not at the equivalence point, that is the hydroxide equals the acid, as long as you're not at the equivalence point, this is the chemistry that happens. Some of the acid will react with the hydroxide, and yes, it'll form water. But the unreacted, and then what happens, of course, is that you form the anion, the conjugate of that acid. But some of the acid will not react because you're not at the equivalence point. So there's going to be excess acid in there. And now in solution, you've generated the common ion through the titration. Now in the initial line, okay, this will react with water and form that and hydronium. So we have to take care first of the stoichiometry, because the strong base will demand a stoichiometric reaction. This is not an equilibrium. This is a one-way arrow. This, however, is an equilibrium. But look what happens. In the initial line, you have the unreacted acid, okay, the amount that was left over because you didn't have enough hydroxide. And then this is the conjugate that reacted to the hydroxide. That's the conjugate that was formed from the hydroxide, NaOH, that was added. So this concentration is essentially the concentration of your sodium hydroxide that you added. You know the concentration of the hydroxide that you add, you know the volume, so you can calculate the moles, and then you can calculate the amount that gets converted over to the product. And if you divide by the total volume, then you have the concentration. So that's the second way that you generate a buffer. You generate it as you're doing the titration. Okay, because some of the acid will react with the base and form the anion. The excess acid that went unreacted will now do its thing, but according to our ice table, you have both the acid and the conjugate that formed from the initial reaction present. You have a buffer. You have a buffer. Okay, so please remember that. It's one of the questions I've asked in the past. Let me go ahead and switch. Okay, this is just more Henderson-Hasselbalch equation. Here's another example. I'm not really going to do these in details because these are just examples showing you, again, the power of the common ion. Here we have, I'm just going to speak and not do any type of writing. Here we have the 0.1 molar acetic acid mixed with, we already did this, okay? We already did this. So yeah, this is a buffer problem, 4.74. So let me move on. Here's an example of the difference when you have a buffer and it's contaminated by an acid. That's the beauty of a buffer. When you have a buffer system, okay, this is a buffer system, and you contaminate it with like a strong acid, like HCl, okay, the pH of that solution is pretty much going to stay the same. It's not going to change very much. That's why we use buffer, because when we have systems and we want to make sure we regulate the pH, we don't want the pH to drift. If it's not a buffer system, a contamination of hydrochloric acid will change the pH dramatically. Okay, so that's why we use buffer systems, especially in medical technology, in biology, and all that. So here's an example that shows you exactly what happens when we contaminate a buffer system with acid and what happens when we contaminate a solution that's not buffered. So here's the first problem. What is the pH of the buffer here? This right here is the conditions for this buffer. I know it's an acetate ion, I know the Ka. Hey, I'm just going to go straight to the Henderson-Hasselbalch equation. The pH is equal to the pKa. The pKa of this is 4.74 plus the log of the, remember, it's the base over the acid. The base is 0.2, the acid is 0.1, and I can get my pH value from that. Okay, that's pretty straightforward. So calculate the initial and final pH that results from 1 milliliter of 0.1 molar added to 100 milliliters of buffer. So now if you add 1 milliliter to this solution, initially it was 100 milliliter, and you add 1 milliliter of HCl, the total volume now is going to go from 100 to 101. Okay, 100 to 101. So what exactly happens? Well, this is what happens. Let me clear this up for you. Like I said, this is the Henderson-Hasselbalch equation in action. Negative log 1.8 times 10 minus 5, that's 4.74. And then you add this term, it comes out to 4.44. That's the pH of the buffer. Okay. And this is what happens when you add hydronium. When you add hydronium, hydronium is an acid. It's going to react with the base. What is the base in that buffer? It's going to be the acetate ion. Hydronium is not going to react with the acetic acid. It's going to react with the acetate ion, the conjugate. So this is what happens. Initially, if we have 100 milliliters and we have a 0.1 molar solution of acetate, then this is how many moles. Remember that when you're dealing with strong acids and strong base, you always have to work with stoichiometric numbers. Stoichiometric numbers means that you have to deal with moles. When you are adding milliliters, especially in the lab, then you don't really want to deal with moles. Why? Because moles is moles per liter. In the lab, you're dealing with milliliters. You're not going to be adding whole liters into a beaker, okay? Otherwise, you need a gigantic beaker. What you're doing is you're adding milliliters. So what you got to get used to is this concept called the millimoles. The millimoles is nothing more than 10 to the minus 3 moles. Okay, so if you take 100 milliliters and you multiply it by 0.10 molar, then that's going to be 10 millimoles. 100 times 0.1 is 10. And you just have to remember, oh yeah, I'm multiplying by milliliters and not liters, so that's just millimoles. And it's going to work out. You got to get used to it. And some of you are going to be resistant, but life is so much easier if you understand millimoles. Okay, so make sure that you know how to do that. Make sure you know. So this is going back to this problem. The acetate ion is going to be right here, the acetate ion, 10 millimoles. The acetic acid is 0.2 times 100, that's 20 millimoles. And then you add hydrochloric acid, that's hydronium, okay? And the hydronium is going to react with the acetate ion. And that's 1 milliliter, 1 molar, it says right here. You're adding 0.1 HCl, 1 milliliter, and then the that'll be 0.1 molar, that's 0.1 millimole. That's 0.1. 1 milliliter of 0.1 molar hydrochloric acid is 1 millimole. 0.1 millimole, I mean. So the reaction is, this is your limiting reagent. You're going to react a certain amount of acetate, okay? And then you're going to produce a certain amount of acid right here. So at equilibrium, when the reaction finishes, you're going to reduce the amount of acetate from 10 to 9.9. Okay, and you're going to increase the amount of acetic acid from 20 to 20.1. Now that's the initial line of your ice table. That's the initial line that you would put in the Henderson-Hasselbalch equation, because that's what you start with when now the acid is free to do its chemistry. You need to first take care of the stoichiometry. But after that, then the acid's going to do its equilibrium thing, okay? And so this right here is the base. This right here is the acid. The volume is 101. But if we stick this into the Henderson-Hasselbalch equation, pH equals pKa, and we know the pKa is 4.74, plus the log of the conjugate base, 9.9 over 101 over the acid, 20.1 over 101. You see how the volumes are the same here? Well, you didn't really need the volume because they cancel out. So you could have just done 9.9 over 20.1. Or you could have actually do the calculation, 9.9 divided by 101, put that number in here, and 20.1 divided by 101 and put that number in there. Anyway, when you do that, guess what? The pH value is now 4.43. The pH value, when it's contaminated by acid, is now 4.43, based on the Henderson-Hasselbalch equation. Remember, initially, no contamination, 4.4. Now contamination, big time contamination, it's only 4.43. It change less than 1/100th of a pH. 100th of a pH. We can tolerate that. That's why we use buffer system. Now, what would happen? What would happen? Let me clear this. What would happen if you had 100 milliliters of water and you add 0.10 molar of 1 milliliter HCl? Okay. Well, initially that 100 milliliter of water would have a pH of 7. Okay. Because remember, we're trying to figure out what is the change in pH. Now, you could certainly do this, okay, work that all out. But what you really need to do is go down to the fundamentals. If you put 1 milliliter of 0.1 molar hydrochloric acid in 100 milliliters of water, isn't that just a dilution problem? Isn't that just a dilution problem? You can do M1V1 equals M2V2. What's the concentration of the hydrochloric acid in that bigger volume? Well, it's going to be 1 milliliter times 0.1 over 101. That's the concentration of my hydrochloric acid when it's diluted. That is this right here, okay? That's that right there. And remember, because it's a strong acid, it's going to dissociate 100%. Don't look for an equilibrium. If you take that value is 9.9 times 10 to the minus 4. 0.1 millimoles divided by 101 milliliters. Again, that's why we use millimoles, because we divide by milliliters and the millis cancel and you get molarity at the end, like magic. Okay. Anyway, you get 9.9 times 10 minus 4 molar. Guess what? If you take the negative log of that number, guess what you get? You get a pH of 3, approximately. So the pH went from 7 to 3 just by 1 milliliter of hydrochloric acid in that water. Whereas if it was buffered, it went from 4.44 to 4.43. That's why we like buffers. That's the beauty of buffers. It resists, and that's why it gets its name, buffers, because buffer means that there's a cushion there, a resistance. Buffer solution resists pH changes. Okay. So the essential feature of buffers is that it removes the hydronium. It removes the hydroxide from solution, because what is pH? pH measures hydronium or hydroxide. If you increase the hydronium or the hydroxide, you change the pH. Buffers will convert that hydronium to something else. Remove the hydronium so that pH doesn't change drastically. So here's a cartoon of what happens. We have a buffer system right here. They don't have to be an equal amount. They could be slightly different amount. But what happens is that when you add an acid, the acid will attack the base and then therefore remove that acid. The base now will form hydronium, and so the conjugate acid. And so what happens is that the conjugate acid will go up and the base will go down. But the key feature here is that you remove H+. You remove H+. And therefore the pH will not change dramatically. Now, what happens if we contaminate it with a base? If we contaminate it with the base, then that base will react with the acid right here. The acid is going to convert over to its conjugate, okay? And so it forms the acetate ion, and the acid will decrease. But again, the key feature here is that the hydroxide is removed from solution, and therefore the pH will not change. That's the key feature. That's what buffer systems do. They take those acids or take those hydroxide, and then through the chemistry, make the conjugate of the pairs. That's why you have to have conjugate pairs. They have to have conjugate pairs because they have to be able to move freely between each other. Okay, so that's a pretty good cartoon in terms of that. And it's important because our blood, the pH of our blood is regulated by buffers. We have protein buffers, we have phosphate buffers, but the most important buffers is the carbonate buffers in our body. It's regulated by carbonic acid and bicarbonate, H2CO3 and HCO3. That's going to be in our system, okay? And the ratio is generally 10:1, carbonic acid to bicarbonate in our system. This is the chemistry that happens. Now look, when we have this right here, then any acid will be attacked by this guy, any base will be attacked by that guy. Again, common ion, right? If we build up too much carbonic acid, okay, if we build up too much carbonic acid, then of course what will happen is that if we build up too much carbonic acid and the equilibrium shifts to the right, then it's going to reduce the amount of hydrogen ion in our system, and our blood pH will go above 7.45. It'll become more basic, okay? The way we eliminate the excess, and then if we build up too much, then sometimes the reaction will reverse itself. The way we remove the excess carbonic acid is we simply decompose it. We basically sweat it out, get rid of it, and we breathe it out. So carbonic acid breaks down to water and CO2 if we get too much in our system. That's the beauty of blood buffer. So when our pH drops below 7.35, our blood pH drops below 7.35, then we have a condition called acidosis. You guys probably already know about this from your biology class. What are the symptoms? Depression of the acute nervous system. You have fainting spell, you could have a coma, and then you could die. Really, okay? What are the causes? Generally, there's two types. Respiratory, that means that you're breathing, have issues, or metabolic. There's some sort of chemistry imbalance in you. Breathing, when you hypoventilate. Hypo means lacking. So you can actually give yourself temporary acidosis. If you want to get out of a medical exam, just hold your breath for a very long time. What happens is that the carbonic acid has no way of being released from your body. So the reaction shifts back in the other direction, this direction right here. So if you hold your breath, this builds up, which means that the reaction will reverse itself and you start generating acid in your bloodstream and you get temporary acidosis. Okay, so that's generally what happens right here. Difficulty breathing because you might have an ammonia or asthma or something that diminished carbon dioxide from being released, or you build up carbonic acid, that equilibrium shift, the pH in your system will go up, you get blood pH less than 7.35. Or you could be exercising, or you could be fasting. When you have fasting, then you have fatty acids that starts breaking down and starts going into your system. A buildup of acid will drop your blood pH below 7.35. So that's the mechanism by which these things happen, okay? If your blood pH goes above 7.45, you see it's a very narrow range, 7.35, 7.45, that's what your blood pH should be. Outside that range, you have some health problems, okay? But if your blood pH goes above 7.45, then these are the symptoms. Overstimulation of the central nervous system, you got muscle cramps, you got convulsion, and eventually you will die. You will die if it's not taken care of. And what are the causes? Well, you breathe too much. You're hyperventilating because you're hysteric, or you got some reaction with a drug, or you've got a fever. So what's going on in terms of the chemistry there is that you're releasing too much carbonic acid. You're breaking it down. Because remember, the sweat and the CO2 comes from H2CO3. It's removing it from your system, which means that acid has to feed that mechanism. Acid has to feed that mechanism. If acid feeds that mechanism, then your acid, the natural acid in your body drops, and your blood pH will be more basic, and your blood pH will be above 7.45. Or you could have metabolic irregularities. And that could be because you're forcing the acid to come out of your system by throwing up, or because you're bulimic. Okay, people who are bulimic will have blood pH that are above 7.45 because they're getting rid of the natural acid in the stomach. Anyway, these are the symptoms. These are the symptoms. So this is the mechanism by which your carbonic acid buffer system works in the body. Okay, I won't really talk more about that. And this is a summary of acid-base chemistry that we've talked about so far. Okay, I want to go in. We're going to be going to at least 6:15 today. Okay, because I want to talk about titration curves, and we'll probably continue on Monday. But